So what we're going to do now is just introduce time as a differential into this. And so instead of having dy dx, it's going to become dy dt. So now these things are in motion. Things are moving. Time is so we're going to have all different boats moving, cars moving, balloons, all different things. Ladders, remember that from last year? Like a ladder moving. It's all things that are in motion. So rates with respect to time. And the question is, as time changes, all other variables are affected. Right, as time changes, all other values are impacted. They are changed as well. Changing one changes them all. So we'll start with a question similar to something you may remember from seeing this before. Trung, where are you at in terms of this? Do you remember, did your summer class get as far as things in motion? Like a very common question would be like a tank of water and the water was draining out, and how did the volume of the tank change? That's probably right towards the end of it. Okay, so we're getting towards new stuff for you. Okay, that's cool. All right. A helium balloon is on the rise. Usually if you see a helium balloon floating away, then you just listen for the sound of a kid crying who just let that balloon go. Oh, my balloon. All right, a helium balloon is on the rise. An observer watches 200 feet away from the release point. At an observation angle increasing at 10 degrees per minute. No, 10 degrees per second. Find the balloon's velocity. Okay, so we need to set up this situation from a geometric standpoint so that then we can attack it from a calculus standpoint. So from a geometric standpoint, here's your balloon. Okay, and your balloon is moving, rising up in the air. And then 200 feet away is a person watching the balloon. So we know that that's 200. And we know that there's a theta, or an observation angle. And maybe we'll call the balloon B. And so it's important to know what's changing about this situation and what is not changing. So as the balloon moves, theta changes, but 200 does not. 200 is a constant. But the relationship between these can be expressed trigonometrically. So what's the relationship between B and theta and 200? Tangent. Okay, very good. So we're going to be looking at the tangent of the angle theta is the value of B over 200. So that's our SOHCAHTOA relationship. And we want to put this thing in motion. And we're going to put it in motion by taking the derivative on both sides. So the derivative of tangent is secant squared of the quantity B. But then we need to apply the chain rule to B with respect to time. So we have dB dt, which is now a velocity. Oh, thank you. We're getting to B on the other side. All right, then on the other side, we'll have the derivative of that, which is going to be 1 over 200 times dB with respect to time, because 200 is just a constant. And we want to find the velocity of the balloon, which means we need to isolate this by multiplying both sides by 200. So dB dt by itself will be 200 times the expression secant squared theta times the value of d theta dt. We know d theta dt to be increasing at 10 degrees per second. So this will be 200 times secant theta times 10. And so this will be 2000 secant theta. And then we are measuring this in feet per second. Feet I know because the 200 was in feet, and the seconds I know because of the value of the time for the changing angle. Okay, any questions on that? So define the expression from geometry. Apply calculus, which is the derivative, to put the problem in motion. Every changing variable will have a derivative with respect to time. And then make sure your units accurately measure what you're measuring. We're measuring dB dt. That's the balloon in motion. So what would I have to know to be able to have an exact value for this? I'd have to know the angle. Okay, I'd have to know what the angle is, or how much time has gone by so that I can figure out what the angle is. I either have to know the angle or I have to know time so I can find the angle so I can figure out the answer to this. Okay, let's try another one. Here's a classic one. We're going to do no, because we'd have to know more information. Yep. Okay, an inverted cone-shaped tank is leaking. And it's leaking fluid at 3 cubic inches per hour. When full, the dimensions are 20 inches tall and 16 inches wide. How fast is the fluid level dropping when the radius becomes 3 inches? There's so much going on in this question. First of all, we have to have an understanding geometrically of what this looks like. So it's an inverted cone-shaped tank. So we're thinking of something that looks like this. shaped like a cone. Filled with a fluid in cubic inches. We know the dimensions across the top, and we know, so when it's full, the dimensions of the height are 20. And what's the radius when it's full? 8. Okay, so that ratio, that proportion, will stay the same all the way down. No matter as the water level drops, so when my water level gets lower, or when my water level drops even further, okay, as the water level drops, the proportions are going to stay the same. And so we know that we're going to eventually get down to a proportion of 3, and we would need to know what the height was at that point. Right? If the radius drops to 3, and what's the height right there? And so we should be able to do a quick little algebra. So R to H is going to be 8 to 20 compared to 3 to H. And we should be able to cross multiply and reduce. So 8H is 60. So H is going to be 60 reduced by 8, which is 15 over 2, which is 7.5. So geometrically, we can figure out the value that we are not given. Okay, also geometrically, we know that the volume of a cone is 1/3 pi r squared h. So we want to put this in motion. We want to start the leaking process, so we want to take the derivative of this with relationship to time. So dv dt is going to be 1/3 of pi times the product rule. So I want to apply the product rule to r squared and h. So I'll keep r squared and I'll have dh dt plus I'll have h times 2r and dr dt. So every variable that's changing is affected by time. The volume is affected, the height is affected, the radius is affected. All right, now we can start substituting in some of the values that we know. dv dt is describing the volume, and we know that this is leaking volume, and it's leaking it at -3, or leaking it at 3 cubic inches, so that would be -3. 1/3 pi. We figured out that we know that the radius is 3, so that would be 3 squared times dh dt. We know that h is 15 halves. At the very beginning, I said that the cone was leaking fluid. Okay. All right, and then 2 times the radius of 3 dr dt. So we've come up now with -3 equals 1/3 of pi times 9 dh dt plus 45 dr dt. The question is asking me to find how fast the water level is dropping. I need to figure out dh dt, but I have this dr dt that is sitting there causing me a problem because I don't have a value to put in for that, and I can't have an extra rate left there. So the clue in that is back to the proportions. The proportions for the original radius and height are the same as the proportions of the rates as well. So going back to the original, 8 and 40 can be reduced to 2 over 5. So R is 2/5 of 8H. The rates are exactly in proportion as well. So if R is always 2/5 of H, dr dt will always be 2/5 of dH dt. So that's going to greatly help me out, because now I can take that knowledge and I can substitute it in for dr dt here. And so that will give me -3 equals 1/3 pi 9 times dH dt plus 45 times 2/5 of dH dt. And so that helps me out so much. Because now I have 9 dH dt added to 18 dH dt. And I can simplify that. So that is super helpful to know that the ratio of the rates are preserved like that. So I'll have 1/3 pi times 27 dH dt, or 9 pi dH dt. And so then dH dt by itself is -3 divided by 9 pi, or clearly -1 over 3 pi. And then the units on that, because we're measuring height and our problem is in inches, this will be inches per hour. So a lot of this is geometry and algebra combined. Not very much calculus. In fact, the only time I did calculus, this was the only calculus line of the whole problem, was the time I did the product rule. None of the rest of it is calculus. It's all just geometry and ratios and algebra. Yeah, I picked one of the hardest questions. They're not all going to be, okay? The one we did before, it only, was only that long, not very much. Okay, this one had way more going on, so that's why I picked it.
So it's just October 1st and finish all stuff for the first semester of Calc AB, right?
Yeah.
I'm pretty sure that after chapter 6, the good life is in.
Oh no, we got 6, 7, 8. We won't hit new stuff till the end of chapter 8. And then the only hard one is chapter 11.
Is that a polar graph?
Well, those are easy. Polars and parametrics are easy. The hard ones are what's called sequences and infinite sequences in series. Taylor and Maclaurin and stuff. That chapter 11 is kicks everybody's butt, but the rest of the chapters are all very doable. Very doable.